So, welcome everybody. This is another tutorial. So, what was just a bit of fun is now going to be turned into a series of episodes. How can it be 22 minutes? Well, it's been running for a while. I had the timer running. So, welcome everybody. This looks like it's going to be a series of streams that was just one stream just to have a bit of fun, that now looks like it's going to be a series of streams where we try and understand. Oh, this chair is driving me up the wall. To learn digital logic. So, in episode 1, I've now renamed it, we learned how to use Karnaugh maps to optimize a truth table, and we used the 7-segment display that I've got on the screen. Yeah. So just before we get going, no worries, mate. No worries. No worries. So just before we get going, this software is called Digital Logic Simulator. Now, if you want to play along, there you go. Right, there you go. I will plonk this in chat. If you want to play along, you can grab the download. It's always best to leave a donation, but you can download it for free if you want to. This is the software we're going to be using. So if you want to join in and stuff, grab the software, because this is what we're going to be using. Also, Sebastian, I think that's his name, Sebastian. He did a couple of videos on he was trying to, he was building Ada, wasn't he, and a display to go with it and stuff like that. So yeah, if you want to join along, then please do. So in episode 1, we took a Karnaugh map, and I've got to remember where it is. Hang on. Oh, can I remember where it is?
I can't even remember where the data folder is for it.
There we go. There we go. So we've got this 7-segment or 8-segment display, 7-segment display, and this was the truth table. Now you guys probably can't see that too well, so I'll just give it a bit of a boost. So this was the truth table. We have 4 inputs, yeah, and for each input was going to light up a segment. So for 0, we're lighting up 6 of the 7 segments.
Hi, John here. Another subscriber. Stay a while. Stay forever.
Who's that? Oh, Docster. Welcome in, mate. Welcome in. 22 months. Wow. 22 months. Welcome, welcome, mate. Welcome. So, if you remember, on 0, for 0, we lit up all the outside LEDs except for 7, and that's why everything's got a 1 in for 7. Yeah. For 1 was just these 2. So, and as you go down, you can see for all the different numbers, and we did the hexadecimal numbers as well. And so we use Karnaugh maps to optimize. So here we go. So this is a Karnaugh map, and what we did was we put the 1s in, and then we grouped all the 1s together in groups of 1, 2, 4 long ways, 4 square. Yeah, and that would allow us then to optimize these things here. So if we use, let's say, if we use one that's not got many in it, which ain't a lot, is it? 5, that one. Let's do that one. Paste. So it takes all these, because you have to combine them all together in a long thing. So there we go, like something like this. Yeah. Combine it into a long, and then we use the Karnaugh map to work out what the optimised, is it optimised? There is a word that they use for it. Oh, what's the mathematical word for it? It'll come to me. But it's to make it so the equation is not so complicated. And then, yeah. Oh, is Saucian whole? Nah, he's not. It's just me and Gary at the moment. And then once we'd optimised it with the Karnaugh map, we went into here and library. So here's segment 1. So if I edit segment 1, then we represented that Karnaugh map as a digital logic process. Yeah. So for segment 1, 0, this is 0, would be on because we're segment 1 at the top, yeah? But if we put 1 in there, it should be off. There you go. So if the number is 1, it wouldn't be lit. 2 should be on. And 3. 4 should be off. Yeah. 5 is on. 6 will be on. 7 will be on. 8 will be on. 9 will be on. 10 will be on because that's A. 11 should be off. Yep. 12 should be on because that's the letter C. 13 should be off because that's D. 14 would be on because that's E, and F would be on. So as you can see, all that process logic controls 1 bit. 1 bit. Yeah. So that was the last thing that we did. How can I get rid of this? Can I? Oh. How can I quit out of this, John? Ugh, I'll do that. Save. I didn't change anything. Oh, I won't quit. Save. Quit. Yeah, I thought it might. So, once we've done all the segments, so all of them are here, look. All of them are here, so we can view that one. So that's the 7 segment one. Once we've done them all, then we created a display driver. Yeah. So we created the display driver. So this is the display driver. So this takes the 4 numbers, runs them through all the 4 bits, runs them through all the segment processors, and then we end up with a 7-bit data bus that will drive an LED display, which is there. So if I go into library and do that, yeah. So this is our 7-segment display. Takes the 4 inputs and the outputs drives the display. So if we do 8, that does that. Yeah. 10 is like that. 11 like that. 1. So it allows us to separate the object that we're trying to control and the input. So that was really fun, and there was a lot of... I did set the homework for people to do it. I don't know how many people did it. I think there was 2 people did it because they shared their projects. But this time we're gonna try and do an adder. Yeah, we're gonna try and do an adder and a subtractor. So the basics of an ALU. Yeah, but it's not a logical unit. It's going to be an arithmetic unit. Don't ask me to say that too fast because I'll get tripped up. And that's what we're going to try and do this time. So we need to start again. So new. In fact, I'm going to quit this and I'm going to do a new project. So stream O2. It would help if I could spell it right. Right. So we start a new project. We've only got 2 built-in gates. So we're going to have to create all the other gates. So we'll do the obvious one first. Yeah. So we'll go in and out. So we're going to do an AND gate. So, in fact, that can be A, B. So we're going to do an AND gate. So everybody should know what an AND gate is. It's that. So we AND it, and then we invert it, and that's it. Yeah, so if either of them are off, it's on, and when they're both on, it's off. Dead easy. Simples, as they say. So, NAND. Right, so, what other gates should we do? Well, OR gate. Right, can I remember how to do an OR gate? Can I remember how to do an OR gate? Yes, as I'm cheating with my crib notes. So A, B, and we'll do the output out here. Just load the last string which has them after. Yeah, I know, but what I'm thinking is, if we can do the basics and then store it away as a project, then we can reload the project back in and start with all the gates all ready for us. That's what I'm doing. So, right, an OR gate is an OR gate, if I remember correctly, is that. If I remember correctly, so... Oh, me and my OCD. So an OR gate is if one is on, so that's working. There we go. An OR gate. How simples. Save. OR. Right, what else is there? What else is there? NOR gate. Well, that's easy enough done. So let's do this. And I can hear Gary's brain whirring. I don't know if anybody else is hearing. I bet he's copying me on his laptop. Your brain whirring, mate?
Not at the minute. We're all right at the minute.
So a NOR gate is exactly the same as an OR
Hello,
gate.
John here. Thank you for following. Hope you enjoy the stream.
Who's followed? Skimnator, welcome. Welcome. So, if any one of these are on, it's off. But if none of them are on, it's on. Right, so, save this one. Ooh, cancel. Cancel, save. Oh. Right. What else? What else? NAND. So we got NAND. No.
XOR.
XOR. Yeah, XOR. Right. New. Right. So let's do this. So A. B. There's supposed to be. Oh. Never. Never. Always on. Always. That's it. Always. There we go. AB. That's better. Out. Right. So XOR. XOR. I have got the XOR. I've got the XOR equation. Right. I don't know if you can see that. I've got the XOR equation there. That's what I'm working on. So let's see if my writing of the equation is right. Right. So according to this, we need an OR gate. We need a NAND gate, and we need an AND. Right. So it's A or B. XNOR. Nah. It isn't, is it?
No, do your XOR first. XNOR you don't use very often.
No, we don't use an XNOR very often, no. Right, so we do this. So we put them both into the AND and the OR, then we AND them both together. So let's do this tidy. Got to get into doing it tidy, because it's going to get complicated soon. And that goes out. Right. So XOR, 2 zeros is a 0, 2 1s is 0, either or is on. So 2 zeros is a 0, either one should be 1, but both should be off. There you go. 1 XOR. Oh, isn't me writing down the equation? XOR. So, is it XNOR or is that how you say it? But it's just an XOR inverted, isn't it?
No.
No. Okay, let's have a look. See what an XOR is then.
It's an exclusive NOR gate.
What's the truth table for that then?
I can't remember it off the top of my head.
Oh, there it is. It is. XNOR is just an XOR, not inverted. Yeah, it's just an XOR inverted. All right.
Yeah, and you use it very, very rarely. It's just one of those gates that I like throwing at people and going, "Oh, what does that do?"
I suppose there is situations where you would use it. Yeah.
There is. I think it's in set reset flip flops, if I remember right.
Right. So XNOR. all logic gates are handy, but you only need NAND. That is true. All silicon chips and all chips are all created out of NAND gates.
I said that ages ago when you made your NAND gate. That's the only one you need.
Yeah, but as in silicon chips, they have templates to do an AND or an OR or an exclusive OR that they then put onto the chips. So they don't individually put the NAND gates on there. They put the NAND gates into a template that's an AND or an OR or an exclusive OR, and then they put that. That's what we're doing. All we're doing is we're just building up the different gates from the core NAND gate, which is what we started with. Yeah. Right. So have I saved that one? I think I have. So and not NAND, and not OR, NAND NOR, exclusive OR, exclusive NOR. There isn't another one, I don't think, is there?
Not in basic gates, no.
Let's have a look. So that's not X, no, or not. Yeah. They're the basic ones. So we should be able to take that lot.
I want to know how that book works.
That what?
That book on that web page that you were just on, where it's got the buttons, and it's the same buttons on every page, but it does every gate as you turn the page over, it changes to the next gate. That web.
Yeah, I'm on the web page now.
Yeah, scroll down. It showed you a picture of a book with bloke pressing some buttons on it.
Oh, that one.
Is it that one? No, was it a bit? It was there a minute ago. It showed you about 4 pictures in a row. Yeah, it probably is that book, actually, looking at it. As it goes through that book, it keeps pressing the same buttons, and different pages works each gate.
Oh, right.
I still can't fathom that out.
There you go. You can see all the different pictures now.
Yeah.
Yeah, just like one of them books that's got the buttons in the back.
Yeah.
It's poking them through the same holes, and each page shows how the different gates work.
I think I know how it works. I think I know how it works, mate.
Go on, then.
Oh, really? Should I tell you what I think?
Go on.
I think... make him buy it.
Yeah, I was going to say, should I get him to buy it?
I'm sure I looked at this before and worked out, I went, yes, and it's actually simple.
Yeah,
I can imagine it will be something so stupidly simple that you can't think about it.
No, it's there, and chat's got it. Chat's got it. You see these holes?
The holes? Yeah.
Well, look, there's 1 for not, 3 for and, 4 for XOR.
It's something to do with them, is it?
So what happens is when you turn the page, you another hole appears. So I bet the sensors detecting the light. So if only one sensor's on, it acts as a NOT gate. So I would assume 2 would be an OR, 3's an AND, 4's an XOR, and it's the sensors that's telling them how many pages they've gone through the book. Yeah. Because these dots won't mean anything to the reader, but I reckon that's those dots are being used to determine which page they're on.
Yeah.
Do you get it now?
Yeah. It's got a little mini microcontroller thing in the back to sort it out.
Well, there'll be there'll be like a credit card SIM type thing on the back, but with very small sensors just to be able to pick up the daylight.
Yeah.
I mean, look at this. Computer engineering for babies. I mean, come on. Those buttons are not going to last 2 seconds, are they? 40-year-old babies, yeah. But I think that's how it does it. Is that those dots tell the controller what gate to simulate. Yeah. Right. That's a slight digression. Right.
I know how you like getting sidetracked.
Yeah. Does anybody remember where these projects were located?
I was going to ask you the same thing because I can't find. I've obviously backed them up somewhere, and I don't know where they're backed up and where they go.
Yeah, can you remember which channel we was talking about this on?
No. About 6 months ago or more, wasn't it?
Yeah.
Maybe longer.
It was fine until the missus came along and tidied up.
It would be under homework, wouldn't it? It's got to be under homework. Where's homework?
Yeah, it probably would actually. That's maybe where we did it, was it?
Yeah, that's where we was talking about it. So let's have a look at homework. There it is. Right, so I bet someone put it on there where it would be. Let me just... I'm winding back. It wasn't that long ago. It was only Christmas time when we did this.
Was it?
Yeah.
That was last year, John.
That was last year.
I thought it was longer than that.
Aha! There it is. There it is. There it is.
What we're looking... Oh, I suppose I could look on here as well, I suppose.
Nah, I've got it. I'm going to pin it. I'm going to pin it. So let me pin it.
What, in homework?
Yeah, in homework. Right, I've just pinned that comment. It's got the Streamo 1 zip in it. You know, the one I've done. But it's also got the path. So let me fire that up so I can zip up. So it's user me. App data, blah, 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 blah. Version and then project. So, right, version 1, projects. There we go. Right, so I am going to zip that up. No, I'm not. I'm going to rename it first. So this is startup. I'm going to call it startup. Yeah, so I'm going to call it startup and then I'll zip it up. So this will be our startup project. Right, now I'll rename it to Stream02ALU. Right, do you see the directory that I pinned? Yeah? Gary?
It's all right, I turned my sound off because I was coughing and I was in the other channel.
Right.
I just had to get back into this one. Yeah,
right, I've just pasted the directory into chat, and I'll also paste it into chat on Twitch. So if anybody's used the same software, they'll be able to go to it. Yeah. And what I will do is I will put this in homework, the startup, yeah? So if anybody's in Discord, this is the startup project with just the basic.
You're putting that in Discord now, that's it,
I'm doing it right now. This is the startup project with all base gates included.
So I'm 10 minutes behind on Amazon.
Right, it's in Discord, mate. I've just put it in there, and I'm going to pin it as well.
Yeah.
There we go. It's pinned. So if anybody's in my Discord, I have just put this startup project. So extract it, rename the directory, and it should appear in here. Yeah? It should appear in here. So just to prove that it does, I'm going to extract that here.
Startup gates. Right.
And if I do load projects, oh, it's not there. Do I have to quit and go back in? Hang on.
Digital logic
it on way in.
Load project. Stream O2 ALU. Open. And I've only got 2 gates and a not.
Well, I've got them all. Hang on, let me do it again, mate. Let me do it again. So load project. Oh, look, here we go. Copy. I can do a copy. Let me do it properly. Hang on. Maybe me zipping it up has not been right. Hang on.
Well, they're there in. Should be there.
Now let me do it because it's not showing on my screen. So hang on. Let me delete that directory and I'm going to delete the zip file. So I'm back to how I was. Right. So copy this and I'm going to call it start up. What did I call it? Just startup, did I?
Startup gates, you called it.
Gates. Right, create a copy. There we go, startup gates. Aha, there it is. Right, startup gates. Zip it up.
If I delete that lot then.
Right, so I'm going to delete this. I'm going to delete the attachment. And I'm going to bang it in there again. And I'll pin it again. There you go, it's there. So that's now me doing a copy. Maybe there is, I bet I'm just wondering if there's a project file that this uses to keep track on what projects it's got. Let's have a look. Yeah, I'm wondering if it's got some sort of tracker. Anyway, so
let's have another game.
Oh. Project folder for Mac people. Oh, thanks, mate. Thank you. In fact, I will copy that and put that in Discord.
But Andy's left. He's going to play with Laura.
Lucky him. We've got him now.
How do you do bold? Is it 2 stars?
Oh, God, now you're asking. I have to keep looking it up all the time.
Yeah, it's 2 stars, mate. I've done it. And I'll pin that as well. There we go. So for Mac users, now know where the project is. And for Windows users...
Well, the only Mac user is gone.
Yeah, yeah. Right.
Nobody else is daft enough.
So, the plan for today is to try and build a simple adder. Yeah? A simple adder. So, let's get cracking, yeah? So if I do new file, and we'll do a truth table. So we're going to be adding 2 numbers, yeah? So, well, if we go to the simplest level, right, it's going to be data carry. carry. And then we're going to have sum and carry out, yeah? Or as I put it, Caffrey. Right, so let's do this. By the way, can you guys see this? Because if you can't, I'll boost it. In fact, I'll boost it. Say again.
I said just about. It's a struggle.
I've just boosted it, mate. Let me know if that's big enough for you, yeah?
Yeah, that'll do.
Right, so the truth table for an adder is going to be 0 plus 0 is 0. 0 plus 1 is 1. 1 plus 0 is 1. 1 plus 1 is going to be 0. Yeah, and then the carry is going to be 0, 0, 0, 1. Does everybody agree with that? Are we going to implement an ALU? That is the end goal, is to try and see if we can create an ALU. Yeah. So do people understand this truth table? How did if you don't, let me know. How did you get to that place? Don't be shy.
You want 2 datas though, don't you? You don't want to carry on the first one.
No, because when you add, you're gonna add the carry as well. Remember, this is the core arithmetic. This is the core adder. So it's a 1-bit adder, yeah?
You're bringing your carry in at the front rather than linking the carry to the second data when you do it.
No, because you've got to carry at the very basic level, mate. You've got to carry in. You've got data in, data out, yeah. But we're calling it data and sum, yeah. And then you've got your carry in and your carry out. If you imagine, doing it in decimal, yeah, like that, and then we add those 2.
Calling it carry in.
Yeah. But the thing is, the first one is 0. The carry will be 0, yeah? Yeah?
Yeah.
Because we've started from nothing, so carry will be 0. But then, after that, 5 and 5 is 10. So that would be 0 down there. But then, we're going to be carrying 1 here, yeah? And then that would get added to that to make 9. And then the carry here is going to be 0 again, because we didn't carry anything across. Yeah? So then it's 6. Oh, I forgot to put the 0 in. And the 0 is going to be again, because 2 plus 2, because it was 6, so no carry. Then 2 plus 2 is 4, and then 0 again. So if 4 and 1. Now, it's not putting the zeros in because it's treating it as a number, so I'll do that. Does that make sense? Yeah?
Yeah, it was just fact. Yeah, now you said it carry in and carry out.
Well, this is the carry in, right? So this is the carry in for this line.
Yeah.
Yeah, and then the end. So we could have carry out down here. Yeah, carry out.
Yeah,
Yeah?
I'm with you. I know what. Yeah, I know what you're saying now.
Yeah? So,
Yeah.
is everybody agreed that looks right for a single bit adder? Yeah?
Yeah, I think Gary's right in where you've got data and carry and sum and carry. Maybe calling the first one carry in and the second one carry out will be easier for people to understand.
Yeah. Is that better for you, mate?
Well, I knew what you meant, but
In fact,
I was just having a long way of saying it.
Yeah, in fact, we'll do this.
That's what I was trying to say, Saucy.
Yeah. How about that? Is that better for you? So data in, carry in, data out, carry out. But the data out is actually the sum. Yeah?
no, I think you were fine with calling the output sum. It's just the carry with having two carries was probably,
Yeah.
you know.
Carry on. Right.
Yeah, carry on adding.
So let's implement this truth table in the logic system. So let's move it over there so we can see it. Move that down. So let's create. So we need two inputs. Yeah, two inputs. So this is going to be data, yeah, and carry in. So I'm going to call it C in, yeah? And then we're going to have two outputs. So this is going to be sum and C out. Yeah?
Yeah.
So, based on this truth table, so let's just concentrate on one thing, is the sum, right? Based on that truth table, using the data in and carry in, what do you think we need to put there to make that come out right?
That's an OR, isn't it? No. Exclusive OR.
And why is it an exclusive OR?
Because your double one is your 0.
Yes. So, to make for the sum bit, all we need to do is put an exclusive OR on. Straight to the sum bit. Right. So, what's the carry out then?
It's an AND.
It's an AND. Yeah? Okay. So we'll put the AND there. I'll try and keep it in. I'll try and keep it as clever as I can do it. Keep it as labelled.
You can join in, Sophie.
Say you what?
I said he can join in.
Who is?
I know, thought he can.
Yeah.
Well, I can, but
Leaving me to answer them all.
Right. So with that truth table, this is our logic circuit, yeah? So when data is on and where no carry is being brought in, we get, so 1 plus 0 equals 1, yeah? 0 plus 1 also equals 1. 0, 0 is 0. 1 and 1 is 0 there, but the carry is set. Do you agree with that?
Yeah.
yep.
Well, there you go. We've done an adder. In its very simplistic form. Yeah? In its extreme simplistic form. So, let's save that.
There's 7 more of them and you've got an 8-bit adder.
Yes. But I don't think they do it that way on on the chips. Not the way everybody was talking, because the way everybody was talking is the next thing is we take this 1-bit adder and we then just trying to remember.
So your first 2 bits got data and carry. No?
I think...
No, your first carry-in's just a 0. Well, you can do it with your first 2 bits to data and carry in, but then you just need to loop your carry-outs to carry-ins all the way down the chain.
Yeah. But the 4-bit adder is adding 2 bits together, isn't it?
Yeah. But the first one doesn't know which bits it's adding, does it?
No.
So it's got to have 0 on its carry. It's got to be a permanent 0 on the first carry.
Yeah, I know, but I'm just trying to think.
You carry flag in the case of a CPU, like.
Yeah, I'm just trying to think where I'm going wrong. Oh, I know what I'm doing wrong.
You need to add 2 bits together and then add that to the next.
Yeah, it's adding 2 bits together. Oh, let's work the truth table out for that then, because I'm not sure. Hang on. So we have got A, B, carry in. Cool. I did all this research and I'm still now questioning what I've written down. In fact, I'm going to do this. B, A, carry in. That'll probably be a better way of doing it. Oops. Why aren't you centered? There we go. Right, so 0 plus 0 plus 0 is 0 and 0. 0, that's 1 and 0. Because I think this is going to go wrong.
Your A and B's wrong way round, really.
Hey? Oh, it doesn't matter, mate. Doesn't matter about that. Don't matter. We're
It
not.
doesn't matter like that.
Yeah, we're not. I mean, if you wanted to get, it would be bit.
I was
0.
just thinking whether it confused you when you went back to your logic board.
Yeah, we'd use it B0 bit B1 bit 0 bit 1. Yeah, that's how we would do it.
Oh, right.
So that would be 0 1. Then that's going to be 1 0 1. 0 1 1 1. Right, guys, do you think that's right?
No. Carry. 1 1 1's carry. Yeah, that looks about right to me. You, so I'll say.
Sorry, I've been distracted. Hold on, let me have a look.
Yeah, I think that looks all right. I think that looks all right.
Yep, it's okay. trying to do 3 things at once.
So this is what we're trying to achieve. Now, using the single bit adders.
Anywhere where you've got two ones, your carry should be set.
Yeah. So let's get our pins. So I'm gonna name them the same as what we've got on there. B0, B1, and carry in. C in. Let's keep the terminology the same. And then here we've got sum and carry out. Right, so let's work this out. So B0 into there, so that's obvious. And the carry should go in there. So that,
yeah, that looks right to me.
oh no, a bit further.
Then your carry out comes round to your carry in.
Yeah, and then this goes out there.
And then no, next one, yeah. So I'm 5 minutes behind you, don't worry.
No. I'm thinking about it myself. So we've got to add this carry out into the next bit. So that's got to go in there. And I'm just looking at the sum.
You need 2 sums out.
No, I think it's this. I think it's that. Oh, that's driving me nuts. That is, my OCD's now gone bonkers. Right, let's try this out. Right, so
No, it can't be an or. It can't be an or, can it? Because if it's A and B, it's all your sum is your sum is a 0.
well, this is why we're going to try it, yeah? So, the first line is 0, 0, 0, which is 0 out, yeah? So,
Yeah.
second line, so keeping this truth table in mind, yeah? So
I think you want XOR.
Say again.
I think it wants to be an XOR.
Well, let's see. So B1, make this 1. We should get 1 and 0, yeah? Which we do. Then if we get B1 and 0, that's the next line, we should still get 1 and 0. Now if we do the 2,
you're going to get
wrong.
a 1 and a 1.
That's wrong.
Yeah, it wants to be an XOR, doesn't it?
No, I'm missing something. Right, I think.
Oh, because it's not adding the second one, is it?
No, that's what I'm. Come on. I think I need to do this.
Ah.
I think I need to do that. But that's still not right.
No, because that carry needs to go into your first adder, and then the output of your first adder, your sum out will go into. Hang on, let me think about this.
Yeah, because we need for 2. We need this. We need the carry to be set. So.
John, you need 2 somehow. You can't get A plus B plus carry in 2 bits. Well, you can actually, but you'd still need another carry out.
Yeah, we've got to carry out.
What?
Because there's only a maximum of 3, yeah? Which is sum and carry together, isn't it?
What was the layout for the adder?
There you go.
No, on the actual adder itself, on the logic thing. I want...
What, the single adder, you mean?
Yeah. Can you bring that up or not? So I can just...
Yeah, can... There you go.
Where? Oh, XOR and into both of them. XOR and and. And the XOR's the carry, isn't it?
Yeah.
How do you rename the pins?
You click on the block at the side here.
Yeah, got it. So there. So there. There.
Hang on.
There. There. There.
Maybe doing a single adder on this is not the right way to go. That's right. So we need that to come out here. But because it's going in there, that's just going 1 plus 0 is equal to 1, and that's not right. So we need, I think we need to get rid of that, and I think we need to, yeah, I think we need that there. What I think. So 1 plus 1 equals sum and the carry. Yeah, that works.
Ah.
Right, so 1 is 1. 1 is 1. Then we get 2. Then that is 1.
A and B into an adder. And then the output of that and the carry into an adder to get your output. But your adder's got 2 outputs on, haven't you?
Yeah. See, that's wrong as well.
Yeah, the old adder's wrong.
Yeah, we've got to take in consideration the carry right at the very start. Can't.
Yeah, you need A, B, and carry to go into 2 XOR gates, and then you use a couple of AND gates and an OR gate to get your carry.
Yeah, hang on. Right, so let's go back to the beginning. So 1 is 1. That's 1. See, that doesn't work.
No. If I think the adder's wrong itself. Because we've only got a 2 input.
Yeah, I think we can't use a 1-bit adder in a 2-bit adder. I don't think we can use a 1-bit adder in a 2-bit adder. Right. So we've done a 1-bit adder, but we can't use it. We can't, because.
Yeah, I think it needs redesigning. Your adder does.
Yeah, but I don't think we can use the 1-bit adder though.
No.
Okay. I have done a 2-bit adder. Mathematically. So this is what I came up mathematically. So I came up with B0, B1 XOR'd, and then XOR'd with the carry.
With the carry.
So
yeah, that'll give you your sum.
Yeah. So this is what I worked out mathematically, and I thought the single adder would, replicate this. Yeah. So that goes in there, and then the carry goes in there, and then this goes to the sum. Right?
And that'll work.
And then for the carry, I have got... so let me do that. Let me redo these Y's because it's going to really knock me off. Let's do that. And do that. And then that can go there, and we'll just bring that down a bit. Right, so for the carry, I've got AND. Right,
A and B.
So I'm ANDing, yeah. So I'm ANDing bit naught. Let's do that again. I'm ANDing bit naught and bit 1.
Yeah.
Then I'm ORing bit naught and bit 1. Hang on, mate. So I'm ORing bit 0 and bit 1. Then that's getting ANDed with the carry. And then the whole thing is all together.
Where's your output from your first AND going?
In there, mate. Right, so that's what I worked out mathematically.
And that works, does it?
Well, mathematically, I've got the equation here, look. Got the equation there.
Right.
Yeah. So, let's try it. So, let's do the first. So, the first line is 0, 0, 0, and we get 0 and 0, which is right. So, 1 is 1 and 0. 0, 1 is 1 and 0. Then 1, 1 is 0 and 1. So far, so good. Then 0, 0 carry is 1. Then carry and 1 is 0 and 1. 0 and 1. And then 1, 1. There you go. There you go.
Oh, you've got an extra gate in yours to the picture I'm looking at.
Oh, you cheated, did you? But it works.
It works, yeah. Yeah. Yeah, you've got an extra OR gate in yours. Because they're taking the sum of B0 and B1 and taking that in straight into an AND gate.
Oh.
Yeah. Well, out the first XOR gate.
Yeah.
That's going into one of the AND gates with the carry bit.
Oh, so they've got a 3-point AND gate.
No, they've got 2 AND gates.
Oh.
But instead of ORing A and B, they're taking the XOR result and then going straight into the AND gate.
Yeah. Tron is going to put the 1-bit adder stays the same, but the second bit gets more complicated. Yeah, that's what it is. Right, okay, so this then is this is a half adder, isn't it? Half adder. But we'll keep it the same. We'll keep it the same. We're going to go 2-bit adder, yeah? So this is a 2-bit adder. So, right then. Four-bit adder. Let's get complicated.
That'll just double them up, won't it?
Right. So let's mark these up. So A0, A1, A2, A3, B0, B1, B2, B3, and then carry in. Yeah? And then on this side, we are expecting 1, 2, 3, 4, 5. So this would be S0. Oops, have I put an extra pin on there? Yeah, I have, haven't I? Oh, can I get rid of it? Get rid of it, get rid of it. Delete. Delete, right. So S1, S2, So S is for sum, yeah? And then carry out. Right then, so let's work this out. So, so we need to add, right, this is me thinking out loud. So this is me thinking that we need to do this. So we add each corresponding bit to the nemesis. Do you guys agree?
I should be taking more notice, yeah. And then you just roll your carries down, out and in.
Yeah. So.
And your last one goes to your last adder.
Yeah. So we roll. It definitely looks like we roll the carry down, yeah. So we put the carry into the first one, and then that comes out and goes into there. That one comes out and goes into there. And then that goes out to there. So these sums now go into their corresponding slots. Cool. Who'd have thought we'd been thinking this much today?
Not me. I did enough thinking at work today without doing it when I get home.
Gary's fault.
My fault. I was only a suggestion because people got involved last time.
Yeah. So right, let's
you just want to do your FPGA thing.
Right. So we got red, yellow. So we'll have red and yellow to represent the two different colours. We'll make the carry. Oh, you git. Carrot. Right. Let's do it there. Blue. There we go. So that's blue, 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 and we'll make the outputs that as well. And the carry can be blue. Right then, so here we go. 0 plus 0 is 0, yeah. 1 plus 0 is 1. 1 plus 1 is 2. 2 plus 1 is 3. 2 plus 2 is 4. That's 7 plus 3 is 10. Yeah, that's 10. 7 plus 7, that's 14, yeah. This should overload it now. Right, so we've got what? 15 plus 7. So that's going to be carry and 6. Is that right?
Yeah, if you count carry out as the next bit up, as effectively S4, that's 22.
Yeah, so 16 plus 2, 18 plus 4 is 22. Yeah, that's right, isn't it? 15 plus 7.
Yep.
So it looks like it's working. So if we max them all out, yeah, and then if we stick the carry in there, that should be the last gizmo.
Looks right so far.
Yeah. We really should stick the LED onto this, and then we'd be able to see the number. But that seems to be right. Okay, let's do this. Right, we'll do the ones. So 1, 2, 3 is 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. That should be 16. Hey, rolled over. Nice. And then 2, 3, 4, 5. Yeah, I think that works. So let's save this 4-bit adder. So that seems to work. So to make an 8-bit adder, obviously, we do these. Cool, this is going to be complicated, isn't it? 1, 2, 3.
You just need lots on the input side.
5, 6, 7, 8. That's the first 8. Cool. I don't know. We might have to overlap them a little bit. So then the second lot. Four, 5, 6, 8. And then the carry. Right, so A0, A1, A2, A3, A4, A5, A6, A7, B0, B1, B2, B3, B4, B5, B6, B7, C in. Have I gone? No, that's right, isn't it? Not, yeah. So, now how are we going to do this? Right? How are we going to do this? I think we need to do this. clearly I can't. My spatial awareness is off by a massive mile. If you right click on the black circle for the pins, you can colour them directly. Oh, instead of the wires. Oh, I see what you mean. Right, so then this no. So then right, okay, so let's put this here. God, I would not be good at laying out circuit boards, would I? Gary's probably cringing right now.
Hey, I just draw straight lines between the pins, I do.
Right, then we want 0, 1, 2, 3, 4, 5, 6, 7 out. Right. It's a pity the colours don't transfer out of the assembly, isn't it? Isn't it? See, the colour's not... Oh, it has. It has. Jump in the gun. Right, so 1 plus 1 is 2. 1 plus right. So that's working.
Well, it should do. It looks right.
It looks right, doesn't it? Right, okay. So let's save that. 8-bit adder. So we've got now an adder. So how
subtractor's dead easy.
Say again.
An 8-bit subtractor's dead easy.
Yeah. So subtract. So if we wanted to do a subtract,
you need one of them, 8 not gates, and that's it.
you put something in chat or something?
No.
Oh, okay.
Yep.
But how is that going?
Right. To do subtraction, it's complement, add together, and add 1. So basically, put inverters on all the B inputs, and carry in becomes high, and that's a subtractor.
Is it?
Basically, A minus B is A and A plus not B plus 1. 2's complement.
Yeah. So the carry
Has to be high.
has to be high.
And all your B inputs have to be inverted.
Right. So the B has to be inverted and carry must be high.
Yeah, I don't know on this how you, because basically you'd ignore the, well, like on a 6502, you have to set carry before you do subtract carry. Yeah.
Yeah.
And that's doing the same thing as what you're doing here, because all it does is do an add.
Yeah. We wouldn't put a carry into a subtract, would we?
No, you can't, because it can't deal with it.
SP, test my carry again.
I think that was a while ago.
All right. Okay, let's do that then. Okay, so let's get our 8-bit adder. Now,
I don't know how you force carry in to be high on this thing, because you wouldn't have it as, well, you can have it as an input, but it needs to be permanently high. And then you just need a bunch of knots.
yeah, I'm just wondering if, in terms of an ALU, yeah, you wouldn't repurpose the carry, would you? You would have a line that says I'm in subtract mode.
Yes.
Yeah, so
But you'd also, inside an ALU, generally you'll have a line that says subtract mode that turns on inverters on all the B inputs.
yeah, and that's what I was thinking. That's what I was thinking. So let's do our 2 sets of numbers again.
Well, that's not worked.
What's not worked?
Mine.
Hang on, mate. Just let me put these on and I'll get the adder back up so you can have a look.
10. 10.
6,
10.
7,
10.
8. 1, 2, 3,
Ah,
4,
hang on.
5,
Yeah, mine's done.
8.
Let me change it to U16.
You found your problem, have you?
I think so. I'm adding it up wrong on I've got my binary calculator on. No, that's still not adding up right for some reason. I'm missing my top 2 bits on my calculator.
Hang on, mate.
16-bit? Because that's adding up to more than 8. Try signed.
What you could do, John, is run all the B inputs through NAND gates and a common line as subtract. I think, if I'm thinking right, yeah.
Right, that's what I'm thinking, yeah?
Yeah.
Right, let's just help Gary out for a sec. Right, Gary, there's my...
Hang on. 1, 0. Yeah, I'm right. It was my calculator that was wrong.
All right, then.
That's a 16-bit there, haven't we? Save. No, 8-bit adder, sorry.
Yeah, it's an 8-bit adder, 16 lines plus the carry, so 17 lines in, 9 lines out, yeah? Right, so for the the problem is...
John.
Yeah.
Make this, rather than this being a subtractor, this becomes a adder subtractor, yeah?
Yes, it's going to be the basis of the ALU, isn't it?
So the submode, call it submode, or call it add subtract or something, yeah. Yeah. Or just mode. Yeah, where it's, if you choose that as being 0 for add,
yeah,
and 1 for subtract, yeah, feed all the B inputs into NAND gates, feed submode to the other gate on all the NAND gates, so it's all common, and you can do the same with carry in. So you need 9 NAND gates.
Oh, someone says the chat stopped working.
Yeah, chat panel stopped working.
I've been having a few problems with the internet. What was the yeah, it stopped communicating with Twitch. What was the last thing that was said? Yeah, I think so. That was a long time ago, wasn't it? Yeah,
It was.
It stopped communicating with Twitch. There we go. Try it now. There we go.
Yeah,
right, so yeah,
just drop one NAND gate in halfway between the two things. Just bear with me. Drop a NAND gate somewhere between B0 and the adder, and hook B0 and subtract up to it. And then we can check my logic.
Yeah, so we'll stick that into B0. So if B0 is 1, it's always 1, look.
Yes, but subtract.
Yeah, but if we're in add mode, which is subtract switched off, that's not going to work.
That's wrong.
Yeah.
Yeah. Hold on. Not. Does it not want to be a NAND? Does it want to? Does it want to be a?
I'm wondering if it needs to be this.
Basically, if it's a 1, we want a 1.
So if that's 1, we get a 1. If that is an, that's inverted it. if I turn that off.
Yeah, that's what you want to do. You need to invert B0 based on...
Yeah, so there you go.
So it is, it's an XOR, not a...
Yeah, so if I turn it off, then it lets it through. But if I turn it on, it inverts it.
Yeah, it's an XOR, not an AND.
Yeah.
Stupid. I'm going to blame the time of day.
No. This is what this is all about, yeah? That we're trying to work. So we need...
And you need to do
1,
the same
2,
with
3,
all of the
4,
B
5,
inputs.
6, 7, 8. We need 8 of those.
And one for carry in. Because you need to do the same with carry in.
Yeah. So let's just try and crush the... Oh, it won't. Well, is it not going to crush them up? Oh, okay. We will then move them down a bit. Right, so B...
Create a new device called 8 input.
Yeah. Right, let's just do this. Oops. There, and there. I'm going to swap the carry and the subtract over. So this is now going to go like so.
Everywhere.
Oh, I should really do it this way, shouldn't I, like that? Then I can do this. Right. Yellow. Let's get these colours done. Right, so these go in there. We'll make them yellow as well. Right, so A7 goes to A7, A6 to A6, A5, 5, A4, 4, 3. I better not run out of space. 2. Go, it's going to be tight. It's going to be tight. Just. Right. So now we need yes, we need one of these. Right, 0, 1, 2, 3, 4, 5, 6, 7, and carry. Right. That's right. 1 plus 0 is 1. Yay. Right. Let's put these in. And then the carry goes out. Right. So 3 plus 2 is 5. That works, yeah? That's working. Add the carry, should be 6. Yep. So, in subtract mode now is 3 minus 2.
Where do you get 3 from? That's 7 minus 2.
Oh, sorry. Yeah. Well, that's right, isn't it? 4 plus 1 is 5, yeah? No, that's not right. Oh, that's 9.
Yeah, 7 plus 2 is 9.
Yeah. Right, so
7
subtract.
minus 2 is 5.
So it should be come back as 5, yeah? But the carry's on.
Yeah.
That's right. That's right, isn't it?
Yes.
Because we set the carry in 6502 and the carry is still set after the calculation.
Yeah, that's working the same as the 6502 adder subtractor.
Yeah. So 7 minus 2 is 5. Yeah, that's right. So if we do
If you put a big number in the D side, it should turn the carry off.
Say that again, mate.
If you put like, I don't know, 100, turn B5 and 6 on in, then it should turn the carry off on a subtract.
And it does. And it does.
Right, so what have we got there then?
Yeah. 192, 194, 198 minus 15. Is that right?
That's 64 plus 8. 72 plus 1, isn't it? 73.
Hold on. No, you've got to think about it the other way around. This is 15 minus 193.
Yeah. Yeah.
Yes, right, SP. We were thinking about it wrong way around. It's A minus B, not B minus A. So it's negative, which gives you the... So should carry out be off? Or do we need to invert carry out? Hold on, let me get a calculator. Oh, that's right. 15 minus 198 is 43 hex, sorry. 49 hex, sorry. So it's the 49 part in hex is right.
193, did you say?
It's 198, but it's 15. Yeah, 15 minus 198 is 49.
It's 49, yeah.
So those bits are right, but I can never remember which way the carry should be.
Well, the carry's right, because if that was done in 6502, the carry would be cleared.
Right. Okay. Well, then it's right. It's like, oh, should the carry be? No. What's missing from it is the overflow. That's what's missing.
Yeah. But that's the thing. How would we test for overflow?
That's a different thing.
How would we test for overflow?
Don't know.
See, so what have you got on there for testing then? Your first 4 bits on A.
Yeah, and bits 1, 2, 6, and 7 on B.
1, 2, 3, 4, 5, 6, 7 and subtract mode.
Yeah, so
And
we
we've
end
got
up with S0, S3, S6.
100, 100, 00. Yeah, I've got the same anyway. I've lined it up right.
Right, so if this is going to be our ALU, right, let's just save this. So this is now our basic ALU, yeah? The first bit is the negative bit, yeah, which is this one. So if we, right, let's just do this. So how is the overflow flag determined?
What does the overflow actually mean then?
No, 15 minus 5 wouldn't trigger an overflow because it's 10. But 15 minus 16 would trigger an overflow of minus... Actually, try that, John. Just turn just put B4 on input and turn others off. Leave A as it is, B4 on.
Hey.
Yeah, that's right. That's minus 1.
Yeah.
But you would have triggered an overflow at that point because you've gone below 0. You've gone 15 minus 16.
Right.
What? Hang on a minute. Oh, yeah. Yeah, I've got the same.
Yeah, because it's A minus B. We started off with doing B minus A and going, oh, that's right. No.
So the negative flag is actually the 7th bit. Yeah, in 6502 it's always the 7th bit, negative flag, yeah?
Yeah.
So
that would be your overflow, wouldn't it?
no, that's just a...
No, that's just saying negative.
Yeah. So the other flag, the 0 flag, would be...
I'm just wondering, does it work if it's carry out odd with XORed with subtract? Because the 0 flag's a different thing. You'd have to OR all the lines together, S0 to S7, wouldn't you?
Yeah, I was just thinking that. So I'm going to do this.
But I'm just thinking, if you XOR, C out, and subtract, does that become overflow? I think so.
I don't know. But what I'm going to do is I'm going to go save. And this time I'm going to go... so we've done the ALU. Now we're going to do the ALU with flags. So I am now going to open ALU with... oh, I can't... oh, that's because I did a save copy, didn't I? Yeah. Right. So I'm in ALU with flags. So what I'm going to do is get rid of that. Get rid of that lot.
How do you save copy?
Hang on, mate. Oh, that's just going to delete one at a time. Oh, really? Right. Just bear me a sec, mate, because I want to say... so here, when you do save, yeah, the save copy. Yeah. So I'm just going to call this 8 bits.
Ah, yeah, I can see it.
16 in, 8 out. Because I'm fed up of typing all those bloody pins. Right, save a copy. Right, there we go. Right, so I'm going to go back to ALU flags. So library, ALU flags, edit. Right, so I need to get rid of that. And I need to get rid of them again. Because this will make it easier now to work with. So now I can put the basic ALU there, yeah, and just stitch everything back up.
Is it worth just making a quick 8 input OR gate on another?
Yes, that's another thing I was thinking of when you said it, mate.
You can just drop one box in and link them all in.
Yeah. Put that there. And that there. And then... Right, I'm going to leave them as they are because we're going to put some stuff there. So I'm going to save this. It's ASU flags. Then I'm going to go back into my 16 in 8. Oops. No. Don't want it. Edit. Library. Edit. Right, here we go. So, right. So we can get... I don't want these. No. Save copy. Right, so this is going to be an 8 OR. 8 in OR. There we go. Save copy. Right, so we're in there now. Right, so we'll get rid of this. Delete. It's a pity I can't highlight it and press delete.
That's annoying.
Yeah. Right, so we've got our 8. So let's just spread them out a bit now.
Just drop 4. Well, 4 OR gates, OR them in pairs, and then OR them again.
Yeah. There we go. Right, so 1, 2, 3, 4. So do that one. Whoops. Do that one. Do that one. That one. That one. That one. And then 1, 2. And then 1.
Just make it a lot easier when you're dropping it on your ALU.
Yeah. Get rid of them. Right, save. 8 in OR. So if we go back now to our AOU flags. So we are going to have some flags. So we've got the carry. Then we want 0. Then negative. Then overflow. So we'd have to work it out, yeah. So let's get all this lot wired up. Just in case I need some space. Are you still with us, Gary? Are you still understanding?
I'm still with you at the minute.
Right. I'm not sure if that's what you're thinking of. Wasn't it a 9 input with each? of the first.
No, we just needed an 8-bit OR gate to produce the 0 flag.
Yeah. Oh, dude, it's not an OR, is it?
No, it's a NOR. You need to stick an inverter on the output.
No, it's not. It.
Yeah, if any bits are 1, then it's a 0.
Yeah. But
So you just need to invert the output.
It's not an OR though, mate, because it means that any one of those bits will flag it as a 0, and it's not.
Yeah, no, that's what I mean. You just need to put a NOT on the output of the 8-input OR gate. So it's always a 0 unless any of them are a 1. Yeah, if all of the inputs are 0, the output will be a 1 then.
Yes. I concur with that. So if we do this there, so we'll start.
Actually, if you go back to edit it, John, you can just put 2 outputs on it and have an inverted output as well. That way it might come in handy the other way around.
Yeah. Well, let's connect this lot up first. Right, so oh my, oh, how parallel are these things, eh? I'm glad I don't develop boards.
Yeah, on board development software, you can have it snapped to references so you can do it parallel.
Yeah.
Oh, that's not doing my. I'm going to say that's not doing my heading. Right, so we OR it. So if any one of these are 1, a 1 will come out. So then we need to
invert it.
Then we need to do that and send that to the negative flag. No, not the negative flag. What am I talking about? It's 0, isn't it? So yeah, let me do that. Get rid of that. So that is 0. So if we go that, then it's not 0. There we go. Not 0. So the negative flag is just basically the
bit 7.
Bit 7. The carry.
Carry is carry.
The carry is carry. So how would you work out the overflow?
I'm sure overflow is basically carry XOR subtract. Because overflow is only going to happen on a subtract, because it's a subtract overflow, not an add overflow. Yeah?
Yeah.
So it's only when you go below 0. So if carry out is 0 and you're in subtract mode, then you've overflowed. No?
Right, so you're saying that we need to XOR this and the subtract, yeah?
Yes, I'm sure.
Okay, let's try it. John, why did you put lines in?
You just have to cross the wires.
Don't cross the streams. Right, so put that in there and the subtract. Right, so I'm going to get rid of that. And then I'm going to do this. There we go. And we are saying this.
Also, and that should be overflow.
And that should go into overflow. Right, so subtract. Okay.
Subtract and carry. You're saying that's overflow?
Yeah.
Yeah.
I'm sure subtract and carry out XOR is overflow, I think.
So it's a small number minus a big number, yeah?
Yep.
So we did that, and it was those two.
A small number
Well, look at that.
minus a big number. But if we've got a bigger number, that seems to work.
Yep. I'm just what Alto Fluff says about negative might need subtract in there. I suppose if you only
No, because you can get a negative by adding if you're working in
you can.
negative numbers.
Yeah, because negative is only a representation of bit 7, isn't it?
Yeah, it's just if you're in minus 127 to plus 126 sort of counting mode, then S7 bit 7 is negative.
Yeah.
But if
It's all.
if you just
It'll
treat
always
it
show
not,
up on the 6502 though, won't it? As negative, whether it's actually a negative or not.
yeah, I think so.
Yeah, it's just a representation of bit 7.
And it's only really used, I think, is it used in, no.
I use it all the time. I use it all the time because when you load, bit 7 goes into the negative flag, yeah?
Yes, it does. So it doesn't care whether you're in subtract mode, it's just a representation of bit 7 state.
Yeah.
And you can treat it as negative if your counting is a plus and minus range. You just ignore it if you're counting in a 0 to 1 to 255 sort of mode.
Yeah.
There we go. We've got an 8-bit adder with
Subtract
flags.
Yeah.
And subtract, 8-bit mathematics unit.
It's a maths unit, isn't it? It's not a logical unit yet.
Now make a multiplier.
Yeah,
what?
Where's your multiplier?
Multiplier? We don't have a multiplier in 6502, mate.
No, but we have one on logic.
But what
multiplier gets more complicated. But for what we want, this is a good start.
Yeah, because to do a logical unit, because we've got to do and or, is we'd have where we got that subtract line, we'd have and or lines that would switch off the maths part and then activate the and or part.
Are we actually going to build a CPU then, do you reckon?
Well, I mean, the simulator, it is possible to do it. It is possible to do it.
Yeah, I know.
But the problem is, you see, we're
limited on real estate.
Well, the fact that we can't zoom in and out really annoys me.
Yeah.
But I was just wondering whether we could fit the or and in here as well. Because we'd need two extra control lines, yeah, to be able to.
We've got room for that at the minute.
Say again.
We've got room for 2 more control lines.
Yeah. So we'd need to create a 16-line AND circuit and a 16-line OR circuit. To because what I'm thinking of is whether
sorry, we'll just also no, the overflow bit is set to indicate that we've gone below 0.
Yeah, the overflow is set when we've used the carry, isn't it? In the subtract. When we've used the carry in the subtract, that's when the overflow flag fires.
Yeah.
See, the negative flag in the 6502 wouldn't be set once we've crossed the 0 mark. Because it's only bit 7 that. So when you negative a big number from a little number, it comes out with a positive number, and that's where the overflow flag comes into it. Because that's how you can say, oh, I'm in negative territory, even though the negative flag is not switched on. But I'm if we do the let's do the and ors, yeah. Let's do the and ors. Let me and I can think while I'm doing it, yeah. So library, go to the 16 in, 8 out, edit. Oh, cancel. Have I not saved? Did I not save that? Save. Right. So going to the 16 in, 8 out, do edit. Then I'm going to do save as. There we go, save copy. So so this is going to be an 8-bit and. Is it an 8-bit and? No.
It'll be.
It's a 1-byte and. It's a 1-byte and, isn't it? We're comparing two 1 bytes together. We're anding 2 bytes together, yeah.
Yeah. That'll be.
Yeah.
No, it's a 2-byte and then, isn't it? Comparing 2 bytes. Yeah. So we'll save the copy for that, and then we'll do save again, but this time we'll say 2-byte or. Right then, so we'll get rid of the carry, and we'll get rid of the subtract, and we'll get rid of that, and we will need a way to switch it on and switch it off. So we're going to need a control line, aren't we? Enable to switch it on and switch it off. Will we? Yeah, we will. We'll need an enable, don't
Well,
we?
you're just thinking about enabling the outputs.
Yes. Yes.
Yeah, just use an enable and chuck everything through AND gates.
Yes. Yeah. So,
or like you've done the 8 input, or make an 8 input AND gate with an enable.
I was just thinking that, mate. I was just thinking that. Right, let me just save that. Right. We'll load. We'll get the 8 in OR. We'll do an edit, and then I'll do save and save copy. Right, so I should be in 8 in and. Right, let's get rid of these. Right, so we want ands. So 1, 2, 3, 4, 5, 6, 7. We need 7, don't we? So 1, 2, 3, 4, and then we need 2 after that, and then 1 after that.
How do you get them multi ones, John?
You press it more than once, mate.
All right.
You press it more than once. And we're only do.
What's this we're making?
Say again.
What are we making here? I needed to go low.
An 8 input and.
No, I wasn't thinking of that, because that's just going to give you a... What's that going to give you? That's just going to give you a 1 if everything's a 1. What I was thinking was 8 AND gates and a control pin, an enable pin. Enable goes to in B on all of them, and A goes to each of them. That gives you 8 outputs that you can enable.
Yeah. Okay. My misunderstanding. And to be honest, when I put it on there and it didn't work, I would realise I'd made a mistake. Well, it's there. It's done. Save. It's done. Just in case we need an 8 input AND gate. Right, so...
Oh, yeah. They're useful.
Yeah, right. So,
what are you going to call it? 8 input.
So let's do the 2-byte AND first. Right, so we'll do that as enable, and then we'll get rid of that. Right, so we are ANDing bits together, aren't we? So our first, so 1, 2, 3, 4. Our first lot is A0 and B0. A1, B1, A2, B2, A3, B3. So that's the first half. So we'll put that up there. Yeah, right, do another 4. 1, 2, 3, 4. So 4 and 4, 5 and 5, 6 and 6, 7 and 7. Right, so we've now got our output. So to make it that the output goes out, we need 1, 2, 3, 4, 5, 6, 7, 8. Where the enable goes. So we'll do that there. And we'll put it in the bottom ones. So we'll put one there, one there, one there, one there, one. I suppose we ought to do this on our maths unit as well, aren't we?
Yeah, probably, yeah, because that way they can all take part.
Yeah. And then these go into their corresponding ands. Wait until we start doing memory. You thought this was bad, Andy, Gary. Wait until we've done memory. I'm telling you, latching is an art form. Absolute art form.
Can you not have another switch in there that does the oars as well, rather than redo it all again? Like you've got your enable, could you have an and and an or switch? So if it was high, it was anding. If it's low, it's oring. I was kind of thinking.
You could. It gets tricky because you'd have to do the same thing again with the enables, and then.
No, yeah, you only use the one enable line, wouldn't you? Because you could take the.
No.
No, because the ALU's right. The reason we're doing this is trying to make a component that does it, yeah? And then we'll drop that component inside the ALU, and then it becomes more than just a maths thing, yeah?
Right, yeah.
Alright. So, yeah, as Alto Fluff has just put it, one chip, one function. Don't confuse. Like we've built up the ALU, yeah, to do, you know, a function. It's like programming. You'd start with the basic things, you make functions, then you build a function of functions, and the program then gets more functionality because of the functions. Same thing here, yeah?
Yeah, that's why I suggested building an 8-input and enable thing. That the part on your right as one device, which you just drop in, was 8 in, 8 out, and an enable pin.
Yeah. Because
you're going to need it again on the OR gate.
Yeah, and we could use it on the maths ALU as well. That we stop the output from that.
Yeah.
So we'll let's do that. So I am going to do. Now there is a name for it, isn't there? There is a name for it, isn't there? It is a buffer, isn't it?
Yeah, in my land it will be, but technically a buffer just is a input equals output. But in my land, an octo buffer would have an enable pin on it. So yeah.
So this is an 8-bit buffer, yeah?
Yeah, for want of a better name, yes. It's just 8 in, 8 out. It's not an 8-bit latch because it doesn't hold the outputs. No. It just enables the outputs, or doesn't.
Or should we just call it 8-bit enabler?
Yeah, that's probably a better way of doing it, because I mean, buffer's not something you really need in this landscape.
No. Right, so we'll do the 8-bit enabler. So I should be in. That's it. I'm in the 8-bit. So we can get rid of these then. Get rid of the pins.
What are you doing? Doing the OR now?
No, we're doing the enabler part. We're splitting the. you know, the and the enable part of and, we're splitting the enabler out because we're going to be using it in more than one place. So what you would do is you create a logic circuit purely to do that enabler so we can drop the component directly onto the landscape, yeah? That's what we're doing.
Now you're confusing me.
No, you'll see. Stick with it, mate. You'll see. Once you realise what we've done, you'll go, oh.
I think I ought to stop trying to copy what you're doing and pay a bit more attention.
Right, so...
Wait for you to upload it onto Discord after the stream.
Yeah, so what you see here, right? Here is where the ands were for the 8-bit ands, yeah? So you should have caught up by now, yeah? So you see when the mouse is moving. And then we add the enabler bit afterwards. But because we're going to use that same enabler technology on other things like the OR functionality and the maths ARUL functionality, we've made a component out of the enabler. Yeah? Yeah,
I'm with you.
Are you with us now, yeah? So I'm going to go back now to our 8, our 2 by and. Our 2 by and. Ooh, cancel.
Yeah, and add that into it.
Yeah, hang on, I've got to save that. Save. Right, and then go back to our 2 by and we're going to remove all these AND gates.
Yeah, that I've just put in mine.
Yeah. And we are now going to drop in our new 8-bit enabler. This new function that we've just built, and we're going to connect it up like we did before in the AND gates.
Yeah.
Like this. So let me connect it up while we're here. See, this is the sort of thing you would buy in a silicon chip that you just put straight on a board.
Yeah,
like with your shifter and stuff like that, yeah? And then we take the enable line.
But it's interesting to see how it actually works.
257, I think.
Hang on, 2 people talking at the same time. Go on, say again. Go on,
So I was just going to say, I think it's 74LS. I think it's 257 is this device, basically.
Right.
357 is a latch version of it. It's ages since I've dealt with them at this level, but yeah.
So
you'd buy that as a piece of silicon with output enable and basically the outputs you could be tri-stated so that they're not driving the bus, etc. But we're not going to go that far.
So here we go. So let's do an AND. So right, so we're going to AND that and this, yeah? And this is the result, yeah? So if we AND that with this, this is our result. Only lines 6 and 0 would active. But because we haven't got the enable line switched on, it's not sending the output out. But as soon as we send the enable line, it sends it out. Yeah?
Yeah.
So now we're going to do the OR. We're going to do the 8-bit OR.
It's all right having all these chips and that, but like I say, this to me is interesting because you're seeing how they actually work inside.
Well, I mean, you can actually do this, and you see the lines that are going in and how it works, look. So if I turn that enable on and then go view, you can see how that component is actually sending the outs out. This is because of what's happening there. I mean, when you go into the ALU and you start digging into it, you can see all the lines all lit up and everything. I thought it was brilliant the way he's done it. Right. So,
like I say, it's interesting to know how these chips work.
Yeah.
That you just You're actually digging inside them, aren't you?
Yep. Right, so ores. So this is going to be an ore. So we're going to go...
and everything that you've built there is built from an and and a not gate.
Yes. That's when your mine does get blown.
It would be interesting to see it decompile it into and not gates, wouldn't it? When you've built a complex chip.
Yeah, shows the whole thing just at its basic gate level.
Oh, the gate level, yeah.
Which is what is happening inside an FPGA when you program it, isn't it?
Exactly, yes.
And this is why I thought it would be useful for you guys who are doing FPGAs.
I would love to, but I ain't got time. I wanted to play with that Commander X16 thingy software, but I just hadn't had time.
That's all right, mate. You'll catch up.
It's annoying because that looks like, oh, I've got some ideas. I could have fun with that. Time.
Like I've got. That's why I can't get into the FPGA. If I got into the FPGA, I'd want to do it, and then I'd be going, oh, what am I going to do now? You know.
We'll stream FPGA every week.
I suppose what I could do is I could find like 3 or 4 hours on a Monday and a Wednesday night to do messing around with Commander X16.
I hope that wasn't a dig.
Not at all, mate. I just think if I didn't sit here taking part, joining in with this, which is, it's good fun. I enjoy the time here. No, all good people, and it's good times. I could be doing something else if I wasn't doing this, but I enjoy this. It's good.
Yeah. Right, that. If I do that.
The only thing is, John gets a bit carried away and sidetracks you off onto a different project to the one you're already in the middle of.
God, don't blame me for that.
Oh, matrices.
You mean the Karnaugh maps?
No, the matrix boards.
Oh, the matrix
boards. I've not even thought about buying one of them.
You mean the LED matrix?
Yeah. That was a big distraction of my time.
Don't blame me for that. You mean that one there? That one there?
Where?
It's on the screen now. That one there.
I ain't got one on my screen.
Bottom right.
That, yeah. It is now. Just come up. That's how far behind I am.
Yeah. Right. So, let's go back. So, ALU with flags. Now, I am wondering whether to take the flags out of this and put it into the component that will put everything in. Because we need to put the enabler switch on that, don't we?
Yeah, and your 0 and your negative need to come out of the and the or sections as well.
Yes, that's why I was thinking about taking them out, yeah?
But overflow and just dog. Overflow definitely has got to stay in there.
It's got to stay in there, yeah.
But your 0 and negative can be further down the chain, yes.
Right, so let's take the 0 out. So we don't need that in there, and we don't need that, but we'll leave the overflow there. Let's get rid of these wires. And we'll put, oh, excuse me. We'll put another one there, which is enable. And put the 8-bit enabler in.
Shall I annoy him, Gary?
Why?
Do you want to swap C out and overflow so you don't have to cross C out line?
You mean like that?
Yeah, then you'd swap the inputs on the XOR gate and C out can go straight to C out and into A input on XOR. And
Yeah.
I just thought it might... If you swapped those inputs, A and B round, you don't need to cross the lines at all there.
Yeah, dear mate. Right, let's do this then. Let's make it tidy. So that would come from there to there, and the subtract line, isn't it?
Right, yeah.
Right. Can I go back to what I was doing?
Yes, you can now. Sorry.
Oh dear. Right. So, if we get a fully functioning ALU unit working, I'll be so chuffed. I will be. Right, if I move that over there a little bit, like that, then I can do this, like that. That should work. Right, so save. Yeah.
I know what John's been doing all day today.
Eh?
I know what you've been doing today all day.
What's that?
You've been watching Ben Eater, haven't you, with his breadboard computer. The first series he did.
I claim the 5th just in case my boss is watching. That must be the last one. So we got ALU with... This is the ALU... Well, this is not the ALU, is it? This is the...
Add subtract module.
It's the math module, isn't it?
At its basics, yeah. It can only do adding and subtracting.
Yeah, but that's what we'll call add, subtract. Save copy.
I think he used most of his was 74 logic though, wasn't it, chips?
Right.
Yeah, that's basically what we've built here. Just a bunch of 74 series, OR gates, AND gates, adders, and buffers.
Yeah. So now I've saved that as add subtract. I can go now to the ALU with flags and now modify this. Yeah. So if I take that out now, that out, and that out. So we need a subtract control line. We don't need enable, but that is now so that will be and if we do another one, which will be OR. So these are the functions now. Right, so let me just move these about. So that's the carry. And then we've got the functions. Subtract, and OR. Right. So, add subtract. We'll do that one first. Put that there, and then we need the 2 by and 2 by or.
You
need another.
Your and and or need to be combined on the input, either or, don't they?
No.
What happens if you enable both of them at the same time?
Well, your computer crashes. That's where your instruction decoder only enables one of those lines.
Yeah. Yeah. Because if you enable subtract and an or, all that'll happen is the data lines will just get merged together. It won't crash it, it'll just merge them all together.
Yeah. So your instruction, you need another line though. You need an enable line for the add subtract module. So you need and or math.
Yeah.
Or something.
Yeah. You're right. So move that up. God, we're getting tight on these. Yoink. Oh, just fit it in.
It's a pity you haven't got a zoom and scroll on it, isn't it?
Yeah. But the thing is, I'm now thinking.
You're going to modify the program.
I'm now thinking of adding another layer. Yeah, I'm going to add another layer. Let me remove that. So I'm going to do save as. So save. And then I'm going to do save copy. But this time we've got add subtract. Now this is going to be and or. Yeah?
Yeah, it probably it'll give you a bit more room, won't it?
Yeah. So we've got and or. So to be fair, it really wasn't designed to cope with very. Yeah, I know. I mean, it's a brilliant program. Don't get me wrong.
It's doing a hell of a lot for a fairly simple little program.
Yeah, yeah. So we don't need them. We don't need them. And we would need.
That's all you need. No, you can do your 0 and what have you later on when you, along with the maths unit output.
Yeah, I don't need to all. Do I need to all these lines together? You know, S0 and S0.
Technically, yes, but since we're not real hardware, you can just join them together, can't you?
I was going to say, can I just join it together and just send it up there?
Don't see why not. Real hardware, you would not do that.
No, you'd have to do an OR, wouldn't you?
Or you'd have to have tri-state outputs on the unit. But yeah, and yeah, we can just wire them together.
Yeah. Let's see if it'll do it. So will that? Yes, that works. Okay, we'll cheat.
It's not really cheating because the logic is what it is.
Yeah.
If you enabled and or at the same time, the output you get is just a right mess, really.
Well, it'd just get merged, wouldn't it? It'd merge the two values together.
Yeah, it'd do what a 6502 does because they cheated on building that, and some lines are literally just linked together, so things happen.
Right, let's give us some space. In fact, I'll give us plenty of space. Put them there like that. Right, so A0, and let's do that. A1, 2, 3, 4, 5, 6, 7. Then we come down there, there, A3, A4. Do you know, when I was thinking about how I'm going to structure this stream, I thought that we would be done and dusted in about an hour. To be honest, because I've actually got the next steps in here just in case we was running out of time. Right. So B now. So if we do B0 like that, B1. Oh, John, you had to screw it up, didn't you? B1, so B0. Oh, that's going to be troublesome. B0, so let's do this. B1, B2, B3, oh, this
It's also
gonna be troublesome. B4.
them B lines that come down, I would have done them the other way around myself.
Yeah, I think so would I, but never mind. But he's done now. Well, nearly done.
Shut up.
Out, mate. I don't think we'll get. I think you're really going to run into problems if you try to build a whole computer on this thing.
It's making the chips too big, isn't it?
Well, once you start adding all the 16 bits of input and 8 bits of output and everything else, it does get quite big. But to actually make it as a working sort of computer unit, you need to start adding clocks, and then you need to start multiplexing address lines and
yes,
enabling and disabling lines everywhere.
Yes.
That's just going to go straight across to enable, John.
Oh dear. Oh, you git. Oh, that was not nice. Oh, I can get it there. There we go. Right. So that's that. I know it looks a bit mess, but there we go. Right. So let's do a quick... Right. Let's do an and. Now, why is that flashing?
Probably because it doesn't like the fact that the output from the OR gate is 0 and the output from the AND gate is a 1. So you may have to chuck everything through an OR gate.
Yeah.
You've got an 8 input OR gate, haven't you?
No, it's an 8. It's an 8 in and 8 out. Yeah. It's not an 8 to 1. It's an 8 to 8. Well, it's actually a 16 to 8, really.
Yeah.
So basically, we need 8, 12, 1, 2, 3, 4, 5, 6, 7, 8. Right, we'll do the 8 first. Oh, why is that still there? Right, so we'll do this. One too many. Gonna do that. So that goes there, 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 there. So in real life, that might have happened in real life then. The alternating.
You would have had outputs driving inputs and horrible things happening.
Yeah.
Wait, no.
You'd be worshipping the magic smoke gods.
No,
What are
no,
you doing?
no, yeah. As soon as you said it, mate, I was thinking, oh, yeah,
You're done.
I'm done. Right, so goes there, 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 and there. There we are. It's not flashing now, is it? It's not flashing. So, yeah. So if I do an OR now, yay! That's right. Yeah. Right. Save that. So
If you turn them both on, we just get a mess.
okay, here we go. Well, if we turn them both on, it should be an OR.
Yeah, basically is, yeah.
Yeah, it's just an OR, isn't it? So, I mean, the computer doesn't crash.
No, it won't. But your output's not going to be.
It's not going to be correct. Yeah.
You should never have that situation because in a computer you would have a instruction decoder that decides it's doing an AND and enables that part of the ALU.
Yeah. Right, so we don't...
Ever impressive.
The phone contains... But never duplicated.
Warlock! Right.
You're going to have to do the same thing with the OR gates on this and then add the 0 and overflow. Not overflow, 0 and negative. That's him.
Yeah, it's just that they're getting big. They're getting big.
Oh, yeah.
How am I going to do this? How am I going to lay this out? Can't rotate them either. Before long, the chip will fill the screen. Yeah. Right. So, I am wondering.
Would you have maybe not been better off creating registers first? So you've got like some sort of memory, so you're only inputting one object into each chip and then 8 output.
No, mate, because you remember we're talking binary logic here, so you're always got lines for bits. So it doesn't matter if you've got let's say if which we will get on to making memory probably in the next stream that we come across, yeah. But you still have to represent the 8 lines. You still have to represent the 8 lines for the bytes, yeah.
Yeah.
So it would be 8 lines going into the memory and then 8 lines coming out. So
Yeah.
you there's no benefit to do that.
Ah, right.
It's not.
Your registers sit before the A0 and B0 areas and feed into there.
Yeah. Right, so you guys had a go at me for my laying out of lines before, so
I'm not having a go at you for out. I think at this point you're at the point where you're just going to join the dots.
It's going to be join the dots, isn't it? I was just trying to think how to lay them out, though.
I'm waiting for him to draw a picture with the lines when he as they're coming across.
So let's start with the difficult ones first, yeah. So we'll go like so. Really, it needs to be a bus, doesn't it? If we was doing this properly, it would be eight lines, but we would have the clock cycling, telling it what to do. On the first tick, get this. On the second tick, get that.
Yep.
It's got a built-in clock in it.
Yeah, but I'm not putting... That's going to be a stream for another day, mate. I mean, to be honest, I thought we would have done this already, but we have been messing around with it. So if I do this now and do that way, like that. Oh, you little... Oh, me and my pre-clicking. Here we go. Diagonal lines galore. And I was trying my best not to do it. There we go. That will do. That will do. Right. So that A1 goes there. That one goes there. That one goes there. There. Crossing lines. Right. So B0. That's B3. Before life was so simple. B5. Oh, hang on. Oh, have I done that wrong?
Just turn B4 on and see which lines light up.
Yeah, I've done that wrong. Yeah. Delete. So, let's delete that as well. So, B4. B5. B6 and B7. Right. So we've got them lined up. So hopefully if I do this, the lines will still be working. Yeah. Right. So this, so we'll make that green. So that can go straight into C in. Subtract. I'll make we'll make these green as well. Subtract. And that goes to enable there. And an OR. Right then. We just need 8 ORs, don't we?
Eight ORs and an 8-bit OR gate that you built earlier.
Yeah. So that one, that one, that one. Do you know, if I'd have had this at school, I would have been brilliant at this. My drawings let me down. As they are today. Right, so we've got the OR. So we need the 8 in OR gate, isn't it?
Didn't you have one of them logic stencils when you was at school then?
Yeah.
Yep.
I mean,
Logic stencil and a flowchart stencil.
Yeah.
Yeah.
I've found my computer books that I used at school. I found them a couple of weeks ago. My drawings are terrible. Even though I had a stencil that's supposed to help, but the problem is, as you can see, I lay them out rubbish. I lay them out rubbish, so they end up being all over the shop. Right, I need to grab that. Oh, I'm just going to go underneath, sod it. There we go, that shows that. And overflow is going to have to come round. Right, so this is the 0 flag, isn't it? So
Yep, that's generating 0. And you want the negative.
Yeah. And we want the negative, don't we? So let me move that up, move that down, stick the negative in there. Yeah, neg. Overflow and 0. Right, so the overflow was subtract XOR.
No, it's already done in the module, isn't it?
Oh, is it? Oh, it is. Yeah. I like easy things. Oh, I've put a pin there. Make that green as well. Right, so the negative is that. And this is everything inverted.
Yeah, we need a NOT gate on it.
Right. So, I'm just going to get rid of that one for a moment so I can do this. So, from there, to there, from there. I will have to scan my schoolwork so you can see all my A's and A stars and all that jazz.
Yeah, all mine got flung in the bin.
It's my mum's fault.
Mine are.
It's my mum's fault. She told me I got to keep everything. She was right, really. Who'd have thought 40 years later I'd be digging it out and showing you guys. Right, that looks like it's all wired up.
It looks good to me.
So,
Now, save that. If you save that now and put that, all that lot, to 2 7-segment displays, it should give you the right answers on the display.
oh, I see what you mean. I see what you mean. Yes, it would. It would, but I don't think... hang on, can we import? See, the 7-segment display is not here. The 7-segment display displays here, but not my... not the
decoder.
Not the decoder, because I've made this stream 1. But yes, you're right. If we put the 4 lines into two decoders and then the LEDs, we'd get the right numbers.
If you was really posh, you'd put the inputs in. Put 4 displays on the inputs as well.
Yeah. Well, let's just try it.
I think you find room for them.
Yeah, so let's do it. Right, 1 plus 1. So we're going to do plus 1, yeah? So we're going to enable maths. It's 2.
And it is not zero.
Zero flag's wrong, isn't it?
Where's the 0 flag wrong? What's going on in your OR gate, John?
Yeah. What's going on with the OR gate?
View on the 18 OR.
Did you put the knot in the OR gate?
No, it's not. It's not. It's not firing up. Look. So we're A1. A1's not fired up.
Well, have you missed connection to the
No,
pin?
it's 8. Oh, it is on A1.
That's definitely going in.
Why is that not working?
I don't know. Let's go. Right, let me just save this. And then we'll go into it, find out what's going on. So it's an 8-bit OR, isn't it? So A1. Oh.
8 in OR.
No, it's not even switching on.
You broke it.
The
We broke the program, added too many gates to it.
I don't know. I'll quit and I'll reload it. So 8 in OR edit. Right. Well, that seems alright. So ALU with flags. So 1 plus 1. Maths. That's better.
Yeah, it's working, yeah.
So,
Yeah.
1
3
minus...
3.5 hours later, we can add 1 and 1 and make 2.
Yeah. Oh, dude, the LED matrix not on, mate. So don't use them, yeah? Right, so if we do, what's that? 1, 2, 4, 8, 9 minus, no, 1 minus 9, yeah? So 1 minus 9, so here we go, subtract mode. We do get an overflow.
That looks like -8 to me.
Where's the calculator? Where's my calculator? Right, so 1 minus 9 equals. That is right, look. Oh, look at that.
-8.
Yeah, -8. Look at that. 3 zeros, rest are on. Yeah, plus the overflow. Ho, 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 ho. Nice. What should we call this chip? The OSK?
Calculator.
Right, okay.
OSK ALU Mark
Yeah,
1.
OSK AL. Right, here we go. Right, so if I turn off math and then we go 1 and we should get 1. But the overflow is on.
Turn subtract off because it wouldn't be on if you've done your decoding properly.
But to be honest, mate, surely the enable line should be in there as well to stop it doing
No,
it.
but subtract doesn't go through the enable, so you can always make it go through enable if
Yeah,
you want to.
that's what I was thinking. So if we had the subtract line on, yeah, we really, yeah.
Just need to put it through
An and, don't we?
an and with the enable line.
Right, let's do that while we're in there. So it's add, subtract, edit. So we need to put an and in there to take that and that. I'll move that down to there and stick that out. Right, so we'll save that. We will go back to that one. So we was doing something like that, weren't we? So we had subtract.
Yeah,
on.
1 and 9 or something, but you
Yeah.
had subtract on and.
Yeah, it's
Yeah,
nice.
there you go. The overflow line's not on now.
Yeah.
If you turn math on, overflow should come on.
Yeah,
Prove it and then turn it off and it should go off again.
yeah. Excellent.
There we go.
So you're right with the decoding, yeah. So decoding would have turned the subtract off. So now we're going to do and. So we should only end up with 1. Oh, look at that. Look at that. And if we do or, we've got a working ALU. Look at that. Let's just do something different. Let's put that on and then do or. Nice. And guys, look, we've got a computer. We have a computer. Well, we've got one segment of a computer. computer chip.
You've got the arithmetic and logic unit of a computer.
Yeah.
The heart.
Yeah. And we've built this out of and not gates.
Which I still think is wrong. What they should have just give you NAND gates and nothing else, and then you make your own AND gates.
Well, Sebastian does say that on his website that
I've not looked.
That people had criticised the fact that he gave two gates when really it should have been just the one gate, which was the NAND gate. But he went and said, ignore the and not, and just make an NAND and then just build everything. I mean, keyboard warriors.
Yeah, it is a bit, but technically, if you're just going to do it like you've done it there, if it just gives you the NAND gate, you can make an AND gate and a NOT gate from a NAND gate. So you can make everything from a NAND gate.
So, what time?
Which we have done pretty much.
Yes. Well, I think the XOR. Hang on. Let me save this just to make sure. I think the XOR was the only one where we cheated, wasn't it? Yeah.
No, you didn't really cheat.
Yeah, it was the. Oh, was it the OR gate that I cheated on?
No, it's not really cheating because
no. It is an AND, but I didn't use. Yeah.
Yeah, you could replace the NOTs with two NAND gates, both inputs linked together, and it's the same thing. It's not cheating at all. It's fine.
Yeah.
There's some interesting stuff, John.
Well, I hope people have enjoyed it. Right. So I'm not going to go on to the next topic, which was memory. How to build memory out of this thing. Because I was confusing myself. I've got it all written down here, right? And I'm just looking at it thinking, how the hell does it do it? How does the hell it does it? So that will be the next stream. So what I'll do is I will zip up this project for stream 2. I'll make a Git repo to put them in. I'll make it public to everyone. I can't see the point in only making it available to patrons. Patrons got quite a lot that's exclusive. So yeah, so I'll make a repo with the zip files in for the projects. So we've made an ALU. So the next thing now is to make memory and registers. Yeah. So hopefully in the next stream we'll have created a register. Because then we have to think about clocks and stuff. I mean, we haven't even put clock on this, because we need the clock to drive this as well, yeah. But I think we might be able to add it at the top level. I don't know. But I hope you found this interesting on how the guys that are paid an awful lot of money making these chips out of little teeny tiny NAND gates, how they have to do it and do lines better than me. Hey, Cellophane.
I just find it fascinating how it all pulls together at the end.
What you mean? How it all? Yeah, it's. Yeah, I mean, when you look at the 6502 emulator or simulator online, and you're running it in, I run it in mega slow mo, trying to understand what's going on, and you're thinking, what on earth is going on here? You look
See,
at
like-
you look at a teeny tiny section, and all you see is going on, off, on, off, on, off.
But I mean, so far what we've done on here is logical. You can see what's going on in the behind the scenes, if that makes sense.
Yeah.
Now, what really baffled me from watching them early Benita videos, the first series he did, was when it came to the instruction set, setting them in when he was building that computer, and he made his own instructions.
Yeah.
Yeah, didn't
Now,
he use
that was-
EEPROM to decode those, though?
No, I don't think he did. Not on the first one, where he actually built the whole the breadboard computer, not the 6502 one, the one before that, the real big one.
Oh,
big one he did.
he was on the real big one, wasn't he? Demonstrating how a CPU works with all the mill steps and stuff like that. Yeah.
Yeah,
I'm
that's
sure,
what threw me with the instructions and that.
I'm sure he still used the PROM to decode instructions.
Yeah, you still got to decode an instruction. Because you have to take the byte and then decode that byte into control lines.
Yeah, but he did that with logic, didn't he, on that?
No, I'm sure he used I think he used two EEPROMs to decode the byte into 14 or 15, because you need loads of different control lines. Because like on here, you need to decode an AND line, an OR line, a maths line, a subtract line. You need to decode store lines, load lines, and read write lines and stuff like that.
But he only did about 4 instructions, though, didn't he, with that big one?
Can't remember. It's a long time since I watched it. Yeah, there was a few instructions.
But what I was...
Yeah, I think he'd only...
Go on.
I thought he'd only got a load instruction, add instruction, and one like a jump instruction or something like that. I don't think there was many instructions.
It might,
I mean, if you just go at that, you've got load, you've got add, jump. You've got to have a condition for the jump.
Wasn't he trying to replicate the Cecil language though? Wasn't he?
I don't know. I can't remember.
That's only got like 8 instructions, I think. There you go. There's the instructions.
You've got load, store, add, subtract. I'm not sure you'd have had multiply and
wouldn't have
divide.
had multiply and divide, no.
Jump if on conditions. So you're going to need at least 6 or 8 instructions to write anything that does anything.
Yeah.
Because then he basically got it to add 2 numbers together from memory and put them on display, or put them on 7 segment, I think it was.
Yeah, because what I was thinking was, instead of trying to build an 8-bit computer, right, I was thinking about building a 4-bit computer. Yeah. So the ALU would be a 4-bit ALU. The register
becomes a lot simpler.
It would make it a lot simpler. Yeah. See, that's what I was going to set as the homework. Yeah, is for you guys to build a 4-bit version of what we've just done. Yeah, because I was hoping for that if we do it right, we'd be able to implement this language. Learn how a decoder works. Learn how the clock governs the decoder. You know, because the decoder is many steps, isn't it? So as the instruction highlights lines going into the matrix, then the clock, the clock stepper would highlight the row, which then fires up the control lines, which then makes it does different things. That's what my understanding of how the decoder works. So,
which is where it becomes a lot easier if you use an EEPROM to do that decoding, because you can use three of the lines, say, as the control line, so you're counting from 1 to 8, effectively, or 1 to, depending on how many steps you've got for each instruction.
Yeah, because if you think about it, the most complicated instruction on a 6502 does it in 4 cycles, yeah? Or is it 6 cycles? 6. Which is the JSR, I think, isn't it?
Yeah.
So that means it goes through 6 steps it needs to do. So it's loading low bit, low byte, high byte. Push, and then jump. So I was hoping we would be able to do that sort of thing eventually once we'd done this. But the homework I was going to set you was to do the same we've done here, but in a 4-bit version. Yeah, because I noticed that Altro Fluff has gone and said if you want to import chips or JSON files, and therefore if you want to import them, you just have to copy what's in the JSON file of the other project into it. And yeah, we can do that. So the LED, the LED decoder, I'm going to try and see if I can import the LED decoder into this, and then we can actually display it. But ultimately I was thinking, could we get a simulator to do these basic instructions? So here we would be doing load, store, add, subtract. We could put and or in there, yeah, and then the jumps, yeah. So jump on negative, jump on 0, jump on overflow. We could add another one. Make sure everything's backed up first. Yes, mate. Yeah. But and then you would understand how the chip then does all the decoding. So we'd have address lines, but with 4 bits, you see, you've only got a maximum of 16 addresses, yeah. But then we could do 8 bits, so it's 256 addresses. But it depends how complicated you want to do it. I think 4-bit, 16 address points, couple of instructions in that memory, and then get it to run through it.
And then get it to play Myriad at the end.
But it's going to take a long time because we don't understand how digital logic works. So we're learning as we're going along. But this is the sort of thing I thought that you would have to learn to do the FPGAs, yeah?
Yeah, because you can. There is an option for drawing it out as a schematic to build the program in an FPGA, as well as doing it in Verilog.
Yeah, but
you can do it with gates on a schematic, and still do it write the program.
Yeah.
So I could copy what we've done here and throw all that onto a big schematic and get it to run it.
Yeah. So, are you going to do a 4-bit version of what we've just done?
I'll have a look, yeah. Probably. I'll got to find a few minutes to play at it, but
anybody else going to try it? Do a 4-bit fully functional ALU?
I'll probably be struggling this weekend.
Yeah, that's my problem. If I had any time at all, it'll be at weekend, and I'm not sure I would. So I'm not going to commit to it. If I get a chance, I will do, John.
Well, I'm not expecting to be done by next week, yeah. But it's just something for you to have a go at and see that, because that will let me know if we've understood it.
Yeah. Yeah, I mean, I'll have a go. Like I say, I just might be a bit tight this weekend for time.
Yeah.
We've got we've got a new sofa coming at the weekend. I've got three Xbox controllers to repair.
It's all that Halo bashing, mate.
Yeah.
What's the utility of converting a truth table to gates? Does someone do that to automate? There is a few out there. I had a look. There is a few out there. If you search, but unfortunately, Sebastian hasn't released the code that he used to optimize what he'd done. But you can do truth table to Boolean expressions. And there are tools out there to do it. Here we go. Truth table generator, online Boolean. I mean, you can do it via expressions, or you can tell it to truth table to logic gates. And there are tools out there, because I was looking at a couple of them. They're okay. But I thought of making one myself using John, it just forgot the name. Using
Python?
no, it's the AI technology, using genetic algorithms. There we go. Using a genetic algorithm, because I have written two genetic algorithms in the past to optimize data, and it's not that hard to do a genetic algorithm once you understand what your fit value is, because then you could send in the truth table and say utilize all these gates, yeah, and then you get the genetic algorithm just to randomly create algebra, gate algebra, and then do a function test. Does it give you what you need compared to the truth table? If it doesn't, you chuck it out and then breed another one, and then eventually, you see, you'd get to the most efficient, and the fit value would be, does we get the right answer? How many gates does it use? And so, and then you're saying, the lower the number of gates, the better the fit. And so you breed then those and see if you can get a lower number. And I think that's what Sebastian used on his. The way he was talking when he says, right, well, I'll leave it now so I can make a cup of tea, which gives me the impression that he was doing a genetic algorithm search on it to get the most efficient. But it's a shame that he didn't release the code for that. I mean, he's released the code to build this. That's why the community version's up and out there where people have tweaked it. But I think the community version, in some respects, has made it more difficult. In some respects, I think they got too feature creepy. To be honest, I've tried using it, and some things I thought, oh, that's brilliant, and then other things, oh, why can't I do that? But so yeah. So
the most important features they haven't bothered with, are they?
Yes. But I don't think it's been touched in years, by the way, the community one. I don't think it's been touched in years. But Sebastian hasn't touched this in 3 years, I think.
And another project for you.
What's that?
Put the features in that it needs.
Yeah, it's Unity though, isn't it? Yeah, it's Unity.
Yeah. Yeah, and you've got to pay for that, haven't you?
No. Don't think you have to pay for Unity.
Thought I had a look at it. Looked at the program, and I thought you'd got to pay for it.
Docster's used it for his game, so ask Docster next time he's on, if he's not on now. He created Trump Towers with Unity. I know that for a fact, 'cause I played it and I can't play it. I die on the second
free, but they changed it.
He'd maybe be the kiddie then to go straight into doing a couple of modifications to it then.
Yeah. There is a license change recently, but I think it depends on the number of expected. Yeah, I think that's what it is. If you're going to sell millions and millions of copies, then they're going to charge you for it. Yeah. But I think for hobbyists, I don't think there is a cost.
No, I think it's revenue based.
Yeah.
It also means the Unity
Docster's
engine.
online, look. Docster, do you have to pay for Unity?
I'm pretty sure if you start making more than so much off of it, then you do. I think.
Yeah, I would understand that. I would understand that because you know you're making a lot of money on free software, and you know I can understand that. But I think the hobbyists, like with Visual Studio, the community editions out there, it's for hobbyists. There we go. No, not before you have earned like $100,000, and then there you go.
Yeah. I think they did some license change where basically they were going to charge everybody for using it, and it got that much of a kickback that they switched it around and changed it.
Well, what they don't want to do is alienate all the hobbyists, because they're the people that generate potential income if they have a game that goes viral. If they have a game that goes viral, then they go, right, you've got to cough up now.
Yeah,
But
that was it. Everybody was going, well, if I'm going to have to pay, yeah.
Yeah.
Like Doctor, if I'm going to have to pay to use it, I'll go and use bloody Godot or whatever.
Yeah. But yeah, I mean, I can and I've got his GitHub repo, so I could download it. I've got Unity, but you know, how many more projects do I want? There you go.
Yeah.
SP's
Ben
just done
Each's
it.
8-bit thing, he did use EPROMs for the address for the instruction decoding.
Yeah. So, I hope you guys have enjoyed the stream. How many people did we have? Well, I don't know. I'm hoping that everybody's learnt something. I hope everybody's learnt something. Like I say, if you want to do some homework, do a 4-bit version of it, because I want to go forward with 4-bit architecture, not 8-bit, because it's just too messy, look, yeah? And see if we can expand the computer thing. So next time we're going to try and build some registers and memory, and then hopefully we can go into decoding. No, I'm not doing 16 bits, mate. Shut up.
Stop making me laugh. I've got your cough.
Yeah, no. You've got my cough.
Yeah.
Yeah.
Just over a week now. Can't get rid of it.
I told you, you shouldn't kiss me over the phone, mate.
Stop it.
Right.
Oh, dear.
Yeah, 8 bits already takes up half the screen. Yeah, I know. Alright then, guys. Well, thank you very much for joining. I hope this is, like I say, a bit of a difference from what we're doing. You know, from the normal coding. But we're going to go back to X16 on Monday and learn a bit more and see if we can make Myriad for the Commander X16. Hopefully in the next couple of weeks, once we've learned how to do things, and then we'll come back to this and on Wednesdays and see if we can do a bit more. All right. Well, thank you very much, guys. I hope you've enjoyed it, and hopefully I will see you on Monday. All right.
Cheers, Jim.
Take care, guys.
Thanking you. See you later.
See you later.
Cheers, folks. Cheers, everybody else who's there.
I'd like to thank all the patrons that are contributing to my channel. Without you guys, I wouldn't be able to do what I'm doing right now. Thank you very much.